got a couple different ones rolling in my mind at the moment. I'm afraid I hit the wrong one here.
So there's no friction?
No, we're not worried about friction or liquid's viscosity.
Where does WA go?
Where did you go?
I see WA, should we have an arrow pointing up for WA too, or did I miss it?
If we put a planet down here.
Oh, okay.
So, if A is in equilibrium, then I know that the force from above has to, plus the weight of A has to equal the force coming from B. So I have FB acting up, and that's got to be equal to the forces acting down. Formula for weight.
Mass and gravity.
Yes, the spirit of what you're saying is right. Somebody want to say it correctly?
Sublimation to gravity.
The formula,
Mass times gravity.
that's closer. Now combine what you two said.
Mass times
Mass
the
equals
acceleration due to gravity.
There we go. You could have also gotten away with just mg. And so I have this force coming up from the top here. I'll just call it force sub. I want to keep it more generic than just air. I'm just going to call it force sub U for upper. It's that force coming from up. And that's going to be the force coming from equal to the force from the bottom. Now, in terms of density, what's the relationship between mass and density?
Density is mass over volume.
So therefore, mass is just density times volume. So instead of mass here of that whole upper section right there, I'm just gonna make a little substitution. So I have this FB is equal to FU plus rho times, so that's the density of A times the volume of A times little g. So just instead of mass here, I put in rho v. Now the volume of it, and just for the sake of simplicity, just assume it's a cylinder. The volume of A should be, well, it's just going to be whatever the area is on top times that depth right there. So if I just take a normal cylinder, what I'm saying is that the volume of this is just whatever the area of this is times the height. So so the force coming up from coming from below is equal to the force coming from above plus the density of whatever A is times my volume of A, which is just what I'll call the cross-sectional area. So the area of the flat surface times that depth, which I labeled as H, times G. Well, if I divide everything by area, I get the force from below divided by whatever that cross-sectional area is equal to the force from above divided by that cross-sectional area plus rho H, we do it in the more traditional order, rho G H. Well, this is force divided by area. What is that?
Pressure.
Yes, this is just the pressure from below. The force from above divided by area? Just pressure. Yeah. So we have a difference in pressure here. PV minus PU is equal to rho GH. So if I take something that is in liquid or in any fluid, is liquids or gases, that there is a net upward force, in this case, a net upward pressure, which would translate to a net upward force, which is related to the density of the fluid times the acceleration due to gravity times however tall it is. If I multiply everything by that cross-sectional area, sort of going backwards. So if I multiply times that cross-sectional area, which I just can write out, I end up with a net force that is upwards. That is the buoyant force. That's the volume of the object, that's the density of the fluid, and that's acceleration due to gravity. So I have a buoyant force acting on me. We've already figured out that my volume is about 0.1 cubic meters. I think it was 0.0999 something. The density of air, what is the density of air? Yeah, I'm gonna have to go off memory on this one. Density of air is very crudely 1 Newton per cubic meter. For some reason I think it's 1.3, but so I'm gonna look that up. The actual number is not really that crucial here, but it's still funny. Seems to be a lot of typing. I'm thinking, if you just typed in density of air, what do you get?
Yeah, but you're getting a lot of crazy stuff popping up, and I don't think it's anything you want. Because if you search up density of air, it gives you a whole graph, and then it says approximately 1.225 kilograms over meters cubed. So then, yeah, I'm still looking.
Oh.
For it.
1.225
I apologize.
kilograms over.
Okay, that makes more sense.
Which does bring up this thing that Hewitt talks about weight density. The only place I've ever seen weight density is in Hewitt's book. So the Newtons was a really careless error on my part. But yeah, weight density, just recognize, maybe it's used somewhere else. Just not in the circles I hang out in. All right, so 1.225 kilograms per cubic meter. That's the density of air. So if I then figure out what is the buoyant force acting on me, the buoyant force is 1.225 kilograms per cubic meter times 9.8 meters per second squared times my volume, which is about 0.1 cubic meters. And if you multiply all that out, you get somewhere around 1. The answer is
1.2005.
1.005,
1.2005.
2005 units. to.
Or Newton?
Newton's the easier one, but it is indeed kilogram meter over second squared. All right, so what if I said my weight was 1,000 newtons? Exactly. Well, the question is, did I take that into account or not? And my actual weight is gonna be 1.2 newtons less than what the scale reads. No, sorry, 1.2 newtons more than what the scale reads, because that's holding me up. So anything that's floating, I've got this buoyant force acting upwards, dependent upon the volume of the object. Again, this is volume of the object that's suspended in the fluid. Now, what's the fluid that I'm suspended in right now?
Air.
Yeah. I will make reference to air molecules. I think I've done this disclaimer before. There really is no such thing as an air molecule, but when I say air molecule, I mean a molecule in air. So it's my volume, acceleration due to gravity wherever you happen to be, and then the density of the fluid itself. So as long as the buoyant force is greater than the weight, or actually if it's greater than the weight, an object will float to the surface. If it's equal to the weight, an object will stay suspended, and if it's less than the weight, the object will sink. So all you need to do to get something to float, like a battleship or an ocean liner, is you need to displace a bunch of water, preferably not in the boat. For those who have Navy experience and know the difference between a ship and a boat, tell me afterwards. So what it does when you sink it in there, it will start to sink. But the more it sinks, the more water it pushes out of the way, the greater the volume that gets pushed out of the way, and the more the buoyant force is. And eventually you reach some balance, hopefully. All right, need to make sure I talk about what I'm going to do with this stuff. All right, I'm going to sort of shift topics now. Into Bernoulli's principle. There's the physicist approach and the engineering approach. Here's the physics approach. As gas moves over, or any type of fluid moves over a surface, the faster it moves, the less pressure there is. If you have an airplane, plane's going this way, so air is coming across it. Air is going to move faster over this wing than it is at the bottom part, because that's horribly drawn. But air is going to come here. It basically, because of the way this is curved, air is going to flow over that faster. As I assume most of you have used a hose before and put your thumb over it, and you get to a squirt farther. If you haven't, you've missed out on a life experience. The same thing going on here. You have air getting squeezed into a tight space, so the air will move faster, and therefore the pressure drops. And so there'll be less pressure up here than down here. It causes lift, and the plane will go up into the air. In throwing a curveball, that's supposed to be a baseball. As you throw a curveball, if you throw a fastball, you put a backspin on it. If you throw a curveball, you put an overhand spin on it. So the ball's going to spin this way as it goes like that. As you've got these strings here that are slightly bulging out. If it's spinning this way and air is coming across it like this, up on top, those little bits of string there are going to hit the air and slow it down just slightly above it. And down below, those little bits that are kind of bulging out from the ball are going to be going with the air, causing the air to speed up just slightly. And so you have a drop in pressure down below, and so a curveball will sink faster. I guess that would be officially a sinker. Or you know, it'll curve off in whatever direction you wish it to, if you're good enough. Then there's the rising fastball, which is actually a myth, but the rising fastball has the idea that if you put a backspin on it, you get the faster air on top. You have therefore a loss in pressure up here, and so there's an additional force acting upwards because of the drop in pressure. The shower curtain. I assume most of you have used shower curtains as opposed to doors that have been attacked by the shower curtain. I got a couple of nods there and a couple people looking at me like, you have no idea what I'm talking about. You probably got those fancy shower curtains that weights at the bottom or something. The idea, the Bernoulli idea, is got a shower here, got my shower curtain unattached. As the water goes shooting down here, it basically causes the air to move faster. As the air moves faster, you get a drop in pressure and the shower curtain comes in. There are a couple more examples in Hewitt. So that's the physics approach. Here's the engineering approach. All of that is wrong. None of that is Bernoulli. Matter of fact, every example Hewitt uses is actually not Bernoulli's principle. It is a pressure difference in each of those cases, but it is not actually Bernoulli. Why not? Bernoulli's principle, actually, if I've got a pipe which narrows down, I got water flowing through here. When it gets to this narrow spot, the water's going to go faster. Assuming I've got some pressure back here that's not going to change appreciably, it has to go faster. It'd be like if you're in traffic and you go down to one lane, if everyone would speed up, and if you go to half the area, half the number of lanes, if you went twice as fast, then no one would ever have to slow down into the crawl. You would never get the traffic backup that you do when something like that happens. Of course, I've had enough cars where I can't go from 55 to 110. Actually, getting above 70 would be one of the rare vehicles I've done. What Bernoulli's principle actually is talking about is the internal pressure here. The pressure here will be greater than the pressure here inside the fluid. The reason why the rest are not Bernoulli is this talks about a pressure difference between two sides of the wing. This is more related to the relationship between the air and the surface texture. This one, I think the last time there was a sort of a contest to come up with the best explanation, the horizontal vortex theory. There's actually, if you go to Wikipedia, the shower curtain effect, they list 5 or 6 different theories that explain it. This one right here is called the Magnus effect. Magnus? I think it's Magnus effect. And matter of fact, the author of the Physics of Baseball says, it's not Bernoulli, very explicitly, it's not Bernoulli. If I meant it to be Bernoulli, I would have actually said it, but I did not. It is the Magnus effect. So, what do you do when someone comes up and talks about Bernoulli's principle, or the Bernoulli effect, when you know clearly it's not? You got some choices. You can just smile and think, what an uneducated buffoon. You could try to correct them. Actually. Or, I think that's pretty much it. You either correct them or you don't. I guess you could just sort of go, and then walk away from the person. That's another option. Cannot right now deal with someone who doesn't understand Bernoulli. Questions here? And it turns out that Bernoulli's principle, there's the math behind it, which I'm not going to go into. Bernoulli's principle is just conservation of energy. Alright, so let's talk about what's happening with 11 through 14. Is that clock wrong? It's only off, split by about 2 minutes. For 11 through 14, I'm going to assign you problems. I'm going to assign it so that each person has the same number of each type, give or take one, such as plug and chug. No one will have 5 plug and chugs where someone else has 1 plug and chug. Everybody will have within one the same number of plug and chugs, same number of think and explain, et cetera, et cetera. The same number, I think at this point I'm only doing evens, but I might throw in some odds, but if there's some odd problems, everyone will have the same number of odd problems, give or take 1, and so forth. I will post it. It is in the homework assignment, so the rest of it you'll sort of pick up as you read, or you'll ask questions, but I was not planning to really spend much more time on 11 through 14. Oh, there's one demo I still want to do. Another one that is Bernoulli, it's actually the Kawanda effect. Just because I think it's cool, and I get to show off something I inherited from my mother. Yeah, you're jealous.
Wow.
All right, I'm holding it up, and then I'm gonna start to tilt it. At some point it will fall. There we go. Air goes rushing around the ball. As the air rushes around the ball, it drops the pressure right next to the ball. Air out here is not changing pressure because air is really not traveling any significance, and so you have this higher pressure surrounding a pocket of low pressure, and so the ball basically, every time it tries to get out, it just gets pushed right back in. Very Godfather 3.
Like a plane?
Like a plane?
Yeah.
Uh,
Like
yeah,
a-
and actually, well, it depends on which theory you buy, but this is known as the Kawanda effect. One of the explanations for airplanes is also the Kawanda effect. So it is like a plane. However, there is another theory called the Lancaster-Frenzel theory. One of them is a Czechoslovakian name, and so I would just admit I did not pronounce that second name